Hi, you're with Christian from AMC and we're looking at Module 9 on electrical systems. So a lot of the work that you're going to be doing on this module is going to be done during the pracs, where you're going to gain a lot of information. But we're going to look at things like component construction, construction of alternators, electric motors. We're going to look at motor starter circuits and move on to switchboards and generator paralleling.
So as we saw in the last module, our alternator consists of a conductor that's rotating between a magnet, and when we rotate our conductor between a magnetic field, it produces an EMF, electromotive force, or a current flow, and the current moves in two directions, and that gives us our AC, or alternating current, which looks something like that, in one direction and another. And we saw that our peak voltage for our single phase AC was 240 volts. Okay, with our three phase, we actually, instead of one conductor, we have three conductors, and being 360 degrees, they're positioned 120 degrees apart. And when we do that, we end up with a waveform that looks like this. It's the same as our single phase, only now we've got three of them. So our waveform will look something like this. So our peak voltage now for our three phase is 415 volts, so we've increased in magnitude. But also, having three conductors, now we've got a much more solid amount of electromotive force compared to our single phase AC. So why do we use three phase AC? What's the purpose of it? What are we going to drive with it? Well, it's going to run our heavy duty consumers, which are three phase electric motors. So things that are going to take high loads, they're things like hydraulic pumps, maybe our steering pumps, some large refrigeration units, deck hydraulics, so things that require a large amount of energy. And of course, we don't use permanent magnets to supply the magnetism for our alternator. We use electromagnets. What's an electromagnet? If we take an iron core and we wrap a coil of wire around it, and then we apply a charge to it, this creates a magnetic field around our conductor here, and that will produce our electromagnet. Also, with our alternator here, we've got a conductor rotating between permanent magnets, or as we said, they're going to be electromagnets. But in an alternator, it's exactly the reverse. As we'll see, we rotate the magnets inside our stationary conductors. So we'll have a look at a bit of a clip of that, and hopefully that will make sense to you. So the electromagnets, or the electromagnetic field coils or field poles, are on the rotor. Here we have four electromagnets or four field coils, and these are be a north-south, north-south. They're two pairs of poles or four poles. There's a four-pole alternator, and then in the stator, or the stationary part, is our conductor or conductors. And here we can see that'll be the start of one conductor and the finish of one conductor. Alright, so here we are with the rotor of our alternator, and we're going to show you a clip in a little while. Hopefully this will help pull it together, but we have what we call our exciter, and this provides the voltage in the form of DC for our field coils. Now here's one. So this is the electromagnet. This is the winding around our soft iron core. So that's one pole or field coil, here's another, and here's another. So this one's a 4-pole alternator on one shaft, our rotor, and the wiring to supply the DC voltage to our field coils comes through along the rotor, and then our conductor coils there in the stator on the outside, and our output is from here. So our output is also sensed from our AVR, the automatic voltage regulator. So that senses part of the output, and it goes through a comparator, and then in our exciter it's wired exactly the opposite to the alternator. So whereas the alternator's got rotating magnetic field poles, the exciter has stationary field coils or field poles, and it has our conductor on the rotor. So this guy, as we said, produces the DC voltage for our magnetic field coils in the rotor, but the AVR is telling these field coils how much voltage to produce to keep these field coils generating the right amount of output. So this one's called the exciter, this one's the alternator. And when we look at it from this angle, we've got our rotating field coils. This one just showed 2 poles or 2 coils, and then we've got our 3 conductors marked A, B and C, red, yellow and blue. And so here is our 3 AC waveforms for each of our phases. So we're looking at a schematic view of our AVR or automatic voltage regulator, and basically here we have, this is the AVR here, and this is our alternator, and it comprises of our exciter on this end and our generator on this end. Now in the middle is the rotor, and on both the ends is our stator, one for the exciter, one for the generator. Now the exciter has its stationary field coils, and from there we induce an EMF into our rotor windings, our conductors, and from there we get an output. We put it through a set of diodes, which are basically one-way valves. It only allows the flow in one direction, and from that we take our DC. And so from here we supply our field coils for the alternator in DC. These are on the rotor, and then in the generator we have, these are stationary field coils around the outside. So we have 3 sets of windings or conductors, and from here we get our 3-phase voltage. 415 volts comes out of here and supplies through our distribution system through to our loads. Now the AVR senses that voltage through this sensing signal here, goes to the automatic voltage regulator, and this determines the output for our exciter field. So this is controlling the output, which eventually will result in the amount of magnetic field strength from our field coils. So the amount of DC voltage going to our electromagnets in the field coils, which will then determine the strength of our voltage output, 415 volts. So the AVR controls the output. Okay, we need to memorize, commit this drawing to memory, and to be able to sketch it up and to explain this system. So if you're struggling with it through the delivery of the course, then don't panic. We can explain this in more detail when you come down to complete the course.
Two of the most important applications of the relationship between electricity and magnetism are the electric motor and the electric generator. By definition, an electric generator is a device that converts mechanical energy into electrical energy using electromagnetic induction. The reverse conversion of electrical energy into mechanical energy is done by an electric motor.
This is a very simple and basic structure of an electric motor. We can see the battery, the commutator, the brushes, the copper wire loop, and the permanent magnet. The brushes are attached to a wooden support, and the commutator is fixed to the loop of copper wire. The commutator rotates freely, rubbing against the brushes. Now, when we pass current through the circuit, this creates a magnetic field around the wire, which interacts with the field of the permanent magnet to produce a rotation of the loop that looks like this. The electric motor and the electric generator are related like two sides of a coin. In general, the task of an electric motor is to convert electrical current into mechanical force. On the other hand, an electrical generator converts mechanical force into electrical current. So as you can see, we can simply rearrange our motor into a generator. In this case, we will provide the mechanical force with a windmill rotor attached to the loop and connect a bulb in place of the battery. We will leave the magnetic field as it is, and as the wind rotates the blade, an electrical current is produced.
Our world revolves around energy. At Doosan Portable Power, powering productivity is our business, and we specialize in building products that put power to work. Our mobile generators transform the stored energy in diesel fuel to electricity for daily use. Let's take a closer look. A generator engine converts diesel fuel to mechanical energy that rotates the crankshaft. As combustion occurs in each cylinder, energy transmits to the engine crankshaft, which generates mechanical power for the alternator. An alternator converts mechanical power into electrical energy in a process called magnetic induction. Magnetic induction occurs when a conductive material such as a copper wire passes through a magnetic field and voltage is produced. If the wire is connected in a complete circuit, the power can be transmitted. Alternators include two primary parts, a stator and a rotor. The stator contains copper coils wound into the alternator's outer casing. The rotor also has wire coils wrapped around an iron core, but unlike the stator, it is attached to the engine crankshaft so it rotates with the engine. When voltage passes through the rotor coils, it creates an electromagnetic field. As the rotor spins, its magnetic field cuts across the stator's conductive wire and generates voltage. Because the magnetic field builds and subsides, voltage fluctuates between positive and negative peaks, which is known as alternating current. The stronger the field, the higher the peaks. Ideally, voltage levels should be consistent so that constant power is provided when under load. To do so, an automatic voltage regulator, or AVR, adjusts the magnetic fields as needed. During heavy power demands, voltage decreases, causing the AVR to increase the magnetic field. Conversely, when power demands are low, the AVR tempers the field. Doosan mobile generators also include alternators with 6 coils wound into the stator. This provides 3 voltage sources or phases. Because each phase combines 2 coils of wire, the sources can be connected in series for high voltage applications or in parallel for low voltage needs. To simplify wire connections, Doosan mobile generators have a convenient selector switch. When an operator selects the desired voltage, the switch adjusts the connections, and current flows through a protective device called a circuit breaker. If current exceeds capacity, the breaker halts the system, protecting the generator and connected equipment from potential damage. Once power reaches the connection panel, operators can attach power cables to the generator's terminal board, receptacle panel, or cam lock panel, transforming electrical energy into light, heat, or motion, providing the power we rely on every day.
Alternators are the workhorse of the power generation industry. It is capable to generate AC power at a specified frequency. It is also called a synchronous generator. Electricity is produced in alternators by electromagnetic induction. To generate electricity in a coil, either the coil should rotate with respect to magnetic field, or a magnetic field should rotate with respect to the coil. In the case of alternator, the latter approach is used. Rotor and armature coils are the two main parts of an alternator. Rotor produces a rotating magnetic flux. Armature coils are stationary. And rotating magnetic flux associated with the rotor induces electricity in the armature coils. This kind of rotor shown here is known as salient pole rotor. For gaining better insight of its working, let's consider a rotor with just 4 poles. Rotor coils are excited with a DC power source. Magnetic field produced around it would be as shown. The rotor is made to rotate by a prime mover. This makes the rotor flux also rotate along with it at the same speed. Such revolving magnetic flux now intersects armature coils, which is fitted around the rotor. This will generate an alternating EMF across the winding. Here is a slowed-down version of rotor-stator interaction. For this 4-pole system, when the rotor turns half revolution, induced EMF takes 1 complete cycle.
So, electric motors, they work on the principle that when you get 2 like pole magnets, a north and a north, or a south and a south, then they repel each other, whereas a north and a south will attract. So with our electric motor, what we do is we have a rotor that has conductors in it. Now these are in bars in between laminated core, laminated steel core. So the conductors are inside the rotor, and then we have electromagnets on the outside. I'll show you a picture of that in a minute. And what happens when we supply electricity to the electromagnets, it creates the magnetic field, which is induces a current, because we have a conductor passing through a magnetic field. Then it induces current into our conductors. Now these conductors then become electromagnets. So basically what we have is a magnet in a conductor, and it's opposed by a magnet, an electromagnet in the field coil. And what we have is like poles that are trying to move away from each other. So, and these are at an angle so that they will start turning in a particular direction as it starts here, and then the repulsion of the magnetic fields pushes the rotor around. And so that's the principle of our electric motor. I'll just show you quickly on another slide. It looks a little bit like that. So there we have our conductors in here, separated by our laminated steel core, and then our schematic of that is we have our rotor with our conductors there rotating inside magnetic field coils. So being a 3-phase, there's 3 sets of electromagnets, and then as we induce a current, as the conductors rotate, they repel each other and push the rotor around, and then we can use that to do work.
Induction motors are the most commonly used electrical machines. They are cheaper, rugged, and easier to maintain compared to other alternatives. In this video, we will learn the working of a 3-phase squirrel cage induction motor. It has 2 main parts: stator and rotor. Stator is a stationary part, and rotor is the rotating part. Stator is made by stacking thin-slotted, highly permeable steel laminations inside a steel or cast iron frame. Winding passes through slots of stator. When a 3-phase AC current passes through it, something very interesting happens. It produces a rotating magnetic field. To understand this phenomenon much better, consider a simplified 3-phase winding with just 3 coils. A wire carrying current produces magnetic field around it. Now, for this special arrangement, magnetic field produced by three-phase AC current will be as shown at a particular instant. With variation in AC current, magnetic field takes a different orientation as shown. From these three positions, it's clear that it's like a magnetic field of uniform strength rotating. The speed of rotation of a magnetic field is known as synchronous speed. Assume you're putting a closed conductor inside it. Since the magnetic field is fluctuating, an EMF will be induced in the loop according to Faraday's law. The EMF will produce a current through the loop. So, the situation has become like a current-carrying loop is situated in a magnetic field. This will produce magnetic force in loop, according to Lorentz law. So, the loop will start rotating. A similar phenomenon happens inside an induction motor also. Here, instead of a simple loop, something very similar to a squirrel cage is used. Three-phase AC current passing through stator winding produces a rotating magnetic field. So, as in the previous case, current will be induced in bars of squirrel cage, which is shortened by end rings, and will start rotating. That's why it's called an induction motor. Electricity is inducted in the rotor by magnetic induction rather than direct electric connection. To aid such electromagnetic induction, insulated iron core lamina are packed inside the rotor. Such small slices of iron make sure that eddy current losses are minimum. This is another big advantage of a three-phase induction motor. It is inherently self-starting. So, you can see here that both magnetic field and rotor are rotating. But at what speed will the rotor rotate? To obtain this answer, let's consider different cases. Consider a case where the rotor speed is the same as the magnetic field speed. Since both are rotating at the same speed, the rotating loop will always experience constant magnetic field. So, there won't be any induced EMF and current. This means zero force on rotor bars. So, the rotors will gradually slow down. But as it slows down, rotor loops will experience a varying magnetic field. So, induced current and force will rise again. And the rotor will speed up. In short, the rotor will never be able to catch up with the speed of the magnetic field. It rotates at a specific speed, which is slightly less than synchronous speed. The difference between synchronous and rotor speed is known as slip. Rotational mechanical power is transferred through a power shaft. In short, in an induction motor, electrical energy is entered via stator and output from motor. Mechanical rotation is received from rotor. Energy loss during motor operation is dissipated as heat. So, a fan at the other end helps in cooling down the motor. Hope you got a good introduction on the working of induction motors. Thank you.
Hi everybody, welcome back to my channel. Today we're going to look at contactors. I've got a bunch of them here, some newer ones, some really old ones, and I want to show you exactly what goes on inside of a contactor. That's what we do here. We carefully disassemble things to show you their inner workings, and then never quite get around to putting them back together. A contactor is a remote switching device that pretty much does the same thing as a relay, except for it's generally rated to handle much higher loads, and they have some unique features. Their most common application is to run electric motors, so that's what we'll be doing here. This is an old school reversing contactor, so it's basically two identical contactors interlocked together on a single frame. One side is to run the motor clockwise and the other side is for counterclockwise. But forget about the one on the right for now. Let's just pretend we have a single contactor. It has a 24 volt AC coil, like most of them do. which pushes or pulls together the high voltage contacts, allowing current to flow to the motor. This one has 3 poles. It's like having 3 separate switches that are all activated by that 24-volt coil. These poles are all independent of each other, so you could use them for 3 separate circuits with 3 totally different voltages. But most of the time, they're all used together to run a single motor. And any voltage you send through the main contacts is going to be isolated from the coil, so you don't have to worry about the high voltage mixing with the low voltage circuit. So here's a more modern contactor with 2 coils and 2 sets of contacts. This one side with 1 coil is a contactor. This is what you would have for a motor that only needs to run in one direction, like a compressor. 2 contactors joined together with an interlocking device make this a reversing contactor for motors that need to run in both directions. Right now we're just going to use one side of it to run this 3-phase induction motor in one direction. I'm going to connect 24 volts to the coil terminals labeled A1 and A2 with a push button to start and stop it. Polarity on the coil terminals doesn't really matter. I'm going to bring my 3 phases from the breaker panel into the terminals labeled line 1, 2, and 3. Now we have constant power coming into the contactor, and when I connect 24 volts to the coil, it will allow that power to go through the main contacts to terminals T1, T2, and T3. I don't know what T stands for, but I know it gets hooked up to the load. And there you have it. I can use a cheesy little single pole switch that's only rated for 1/4 of an amp to run a 3-phase 460 volt motor that runs at 20 amps. Here's the schematic for what we've done so far. We have the 24 volt coil with terminals A1 and A2. We have our 24 volt power supply and a switch to make or break the power to the coil. This is our constant 460 volts from the building power in 3 phases. This is the motor with its 3 terminals, and these are the 3 poles of the contactor that will open and close together when the coil is energized. This dashed line represents the magnetic force from the coil that pulls the contacts closed. So when I energize the coil by pressing the push button, it closes the main contacts and connects lines 1, 2, and 3 to the motor's 3 windings labeled 1, 2, and 3 respectively. If I were to swap any 2 of the 3 phases, the motor would run in the other direction.
Hello, I'm JW, and in this video, circuit breakers. Here's an example of a Crabtree one, but they're all pretty much the same. And these devices are there for 2 reasons. They're to disconnect the supply in the event of an overload or in the event of a short circuit. Now, these are fairly ordinary circuit breakers, so these are Crabtree branded, but again, they're all going to be pretty much the same design. And these ones have the plug-in arrangement on the back. Most of the others actually have a screw terminal at the bottom. These just have that sort of pre-made piece which plugs into the corresponding part in the consumer unit. And they've got the usual terminal on the top there for the wires going to the circuit. And these are just single pole devices. The power will be connected in at the bottom, so you'll normally fire a screw there, or in the case of this one, the tab on the back, through the mechanism inside, and then your outgoing circuit will be connected at the top here. And this particular one is a 6 amp device, so typically that would be used for a lighting circuit. And there's another 6 amp one here. This 40 amp one was actually for a cooker circuit, and then there's another 6 amp one over there, which again was for another lighting circuit. Now, these things of course have a switch inside. These are all on the on position, and obviously in the off position it just disconnects the 2 terminals so that the circuit is no longer connected to the power. Okay. So here on the side, and so this other half is just a plastic moulding, so all the actual mechanism is in this half. And so just remove that piece and just turn this so then we can have a closer look at that. Right, here's inside the device, and the incoming connection is at the bottom here. This particular one has a sort of plug-in tab there which comes via the metal pieces here. Most types actually have a hole in the bottom here where a prong or wire would go in, and then there's a screw terminal kind of arrangement here, but in any case the power comes in at the bottom, and the contact is actually here, shown in the open position here, and it's between here and this movable piece here. So if I just move the switch there, you can see that will now close. So that's the actual switching part of the device. So assuming it's in the closed position, we'll come across to the hooked piece there, and it's actually connected to this piece of braid on the back there, which is not terribly easy to see, but that comes across onto the braid there, and then you've got a thinner wire there which forms part of this coil around this movable piece in the middle here. And this is basically a solenoid, so that when that's magnetised, this pin will move forward. And of course continues via all the wire there, and it comes out at the top here on another sort of braided connection piece there. Let's put that back in. And the braid actually connects to this movable piece of metal here. And this is a bimetallic strip of the type also used in thermostats. And current continues via this strip here, and then comes back via the terminal and of course out to the circuit wiring that you have. And the screw here is just used to tighten up and pull onto the wire so it's secured in position. Now these things have got two tripping mechanisms, and the first one of which is this coil here. And essentially when the device is in the on position, just place it there, of course current is flowing through this all the time, and in the event of a short circuit, the current that flows here will be extremely large, typically in the order of a few hundred or even several thousand amps, depending on the characteristics of the supply. This will create a magnetic field here, and it will move the pin there, and in this case it will push upwards, and on pushing upwards onto this piece here, it will cause the device to trip, and of course open the contacts at the other side there. So let's try and show that again. So contact closed, and when this is pulled up, springs open, and of course opens the contacts, disconnecting the supply. Now the other tripping part here is this strip, and this is a bimetallic strip, similar to the type also used in thermostats, and as the current passes through here, it will cause the strip to heat up, and because it's made of two dissimilar metals, one side of it will expand at a different rate to the other. This will cause the strip to bend, and as it bends, of course, it will pull on this little lever here, and if it heats up enough and of course bends far enough, then it will cause the device to trip and switch off. And of course this is selected as depending on the rating of the device, so that if the current exceeds a predefined level, then of course that will disconnect the device. And this is the part which would typically react to smaller types of overload. So say for example on the 6 amp circuit breaker we have here, if say 10 amps was passed through it, and of course that would slowly heat up and cause the device to trip. Hello, I'm JW, and this is one video in a series about protective devices as used in electrical installations. In this particular video we'll be looking at RCDs, or residual current devices. This is a typical example as you would have fitted inside a consumer unit. Again, I've got the line and neutral in and line and neutral out on the other side, and just a switch there for the manually turning it on and off, and the small test button which you'll find on all of these devices. You can also get these to fit on the end of extension leads, for example. Here's one that wires on permanently. Again, it's got that test button on the front there. You can also get these in a similar style with the plug there and a socket on the back, so you can of course use that with any other appliance you might want to do so. And these devices are only there for one purpose, and it's to disconnect the supply in the event that current goes to places that it shouldn't, such as if someone touched a live wire, or you slashed through the wire of your hedge trimmer and it trailed in the grass. And these are also the devices which are primarily there to protect people rather than the installation itself. So we'll have a look at some of these devices, and more importantly how these things actually work, and why really you should have these inside your house. Now here's a typical example. This particular one's made by British General, but they're all pretty much the same in design. You've got, in this case, two terminals at the top here for line and neutral, that's the supply in, and at the bottom line and neutral out. And these will always have a connection to both line and neutral, because they work by monitoring the current flowing through the device, so obviously through the line and then returning via the neutral. And in normal circumstances, of course, those two currents should be exactly the same. If a fault occurs on the load side of the device and the current can then flow to earth via some other path, the current flowing through here is not going to equal the current coming back, and in those circumstances the device will trip and disconnect the supply. Now all of these have a test button on which basically simulates a imbalance in the current. That's just to make sure that the thing will trip, and if you press the button and it doesn't trip, then of course that would indicate a fault with the device and it would need to be replaced. Now this is a single phase device, it's just got the single line on this side of the neutral here. They are also available in a three-phase variety. This is a WILEX model, and again the similar principle applies, except in this case you've got the 3-line inputs here and the 3-line outputs, and again the neutral over that side. So in this case it's 3 phases coming in, 3 coming out, and of course the neutral for any current on the return. But again they work in exactly the same way. Same test button, and it's just obviously a physically larger device purely to accommodate the extra number of connections. Now it's important to note that these devices do not react to overloads or short circuits. Most of them will have a rating on the front here, in this case 63 amps, but that's just a rating of the internal contacts and switching mechanism. That does not mean it's going to suddenly trip out when you exceed 63 amps. You could put 200 amps through this device, it won't trip or do anything. Again, if you shorted out the supply and several thousand amps flow through it, again, it's not going to disconnect at all. That's purely there as a maximum rating of equipment you can connect downstream of it. In this particular case, the 3-phase one, so it's actually only rated to 32 amps maximum. But again, it's not going to trip on 32 amps because it's simply not designed for that. The information of interest on these is the rating here, which in this case is 30 milliamps. And this is the amount of imbalance that needs to occur for the device to trip. So in this case 30 milliamps or 0.03 amps. And the other information is primarily the breaking capacity of the device, which we'll cover in another video, the voltage of course and the frequency, and obviously the various standards to which the thing is manufactured.
Let's talk about our distribution systems. So we're talking about our main switchboard and our distribution boards. We have our generator 1 and generator 2. We can call them alternators, alternator 1 and alternator 2, or genset 1, genset 2, all same thing, different smell. Okay, so this is powering what we traditionally call here would be our bus bar. In the early days I called them buzz bars because of the electron flow through there. They would kind of buzz, and they called them bus bars, which are often in a lot of systems they're a live big copper bar there, and often they're uninsulated, which allows for heat distribution or dissipation within the switchboard. Here we're showing an X as a circuit breaker, so circuit breaker from each of the generators through to our main bus bar or switchboard, and then from there through other circuit boards to our distribution network or sub boards, and here we've got other load consumers. This one with 2 circles intertwined, that shows a transformer, and we'll have a look at, here's another system, a distribution system. This one's all DC though, so there's no, the alternator is actually producing DC, 24 volts DC, and this is going through to our main distribution system, shown through a fuse and a circuit breaker to our different loads, and it's also got a battery system which is also 24 volt DC, so batteries in series parallel to supply our main distribution as well if the alternator stops or the main engine stops. We've also got a starter motor from our battery supply to start the engine to run the alternator, and from here we've also got a transformer down to 12 volts for our nav lights and a 12 volt house battery bank. Okay, that's for our DC system. Let's move on to what it might look like for an AC system. So here's our main distribution board, our main switchboard, and it's being supplied from one of 2 diesel alternators or gensets, generators, and from here we have our 3-phase load distribution, so off to our main services. So for our 3-phase systems, refrigeration, deck machinery, our steering gear, things like that, our large consumers. And we're also, here we are going over our steering gear. This is a motor starter panel supplying a 3-phase electric motor for a seawater pump. So all of these are 3-phase systems. Here's another motor starter supplying our fire pump. And from here we're also going through to a transformer down to our single phase. Now this one's 220, we use 240 volts. It's supplying our lights, nav lights. They can be 240 or often 24 volts DC. And we've got another distribution board here in the galley for our single phase equipment, 240 volts. And then we've got our DC system, so a battery charger here supplying our batteries at 24 volt, and then we've got a 24 volt distribution board which is supplying all of our DC equipment, our emergency gear. So let's have a look at how that might look in a schematic drawing. So bear with me. Alright, so I'm going to sketch that same system up but in a schematic drawing. So I'm going to draw in 2 alternators and through a circuit breaker and down to our main distribution board. Now from there we're going to power our 3-phase load consumers. I'll just draw a few in there. So things like our steering, 3-phase steering motor, our refrigeration, and we've got a 3-phase motor powering a hydraulic pump for an operated deck winch. Okay, now we are also going to have a transformer. So this is all along here is 415 volts, 3-phase. So after our transformer we transform down to 240 volt single phase system, and from here draw in some circuit breakers, and here's our 3-phase load down to our general purpose outlets or power points, and things like our lighting, any other single phase load consumers for cabins. Okay, and then on this end we're also going to have a transformer and a rectifier. What does a rectifier do? That changes the state. So we drop the voltage through our transformer down to 24 volts, but we're also going to change its state from AC to DC, and then that is going to supply another distribution board for all of our 24 volt emergency equipment. So things like our emergency lights, our nav lights, nav equipment, and then from here we're also going to have our battery bank, and we're also going to have a static charger which is going to keep our batteries charged. Often this is the way this system works, that it runs on the higher voltage. We set our transformer slightly higher voltage than what our battery voltage is, and the supply will be from the transformer. And in the event of a blackout, if we lose our genset or gensets for any particular reason, then we automatically have DC power straight from our batteries to our emergency systems. And so we've named a couple of those, and they call us a bumpless transfer. So in the event of blackout, we don't have to wait for any changeover. There's no interruption in power. The power just comes straight through to our system. So what sort of equipment do we power with our emergency battery banks? Well, I'd like you to pause right now and see if you can answer this question as if you would in an orals, and see how many items you can get, the important equipment. Alright, I'm going to answer you now. So, we're going to power things like our emergency lights. So this is all in the event of a blackout. What essential equipment do we need running? We also need our navigation lights. We want to have our nav equipment. Now, depending on the vessel, might be different things. Definitely radios, marine radios, perhaps radar, depends on the vessel, and some other bridge equipment. And we also want to power some alarms. So what are the essential alarms that we want to have? We need to be able to have our bilge alarms indicated to us. We also need to have our fire alarm detection panel operational, and we may also want our machinery space alarm panels, so we know what's happening to those. So memorize these, and also I need you to memorize the distribution system. There's one in your book. Look at the one that we just previously had drawn for you and commit that one to memory.
Gaan we eens met de speed. Auto.
The process of paralleling or synchronizing two generators or two alternators is essentially this, where we have one generator which is on the board and it's producing our three-phase AC 415 volts, and you can see the three phases here as blue, black and red. Now if we want another generator to come on and operate powering the board at the same time, then we need to parallel or synchronize the alternators. And to do that, the black phase on the incoming has to start at exactly the same point. If they're any little bit out of phase, then it's going to do destruction to the switchboard or some of the gear, perhaps even the alternator. So the black phase has to come in at exactly this point, the blue phase has to come in at exactly this point, and the red phase. All three of the phases have to be synchronized at the same time. Okay, so what does that look like? Well, this is a typical kind of setup that we might see. Here's one alternator or one genset, there'll be another one over here, and here we've got the port generator here, and this is the board for the port generator. Here'd be the one, here's the one for the starboard generator, and right in the middle we have a synchronization panel. So when we parallel, we can have both the port and starboard generator on at the same time. Here's roughly the panels we were looking at in that picture. We've got generator 1 here, panel here, generator 2, panel here, and we've got a synchroscope in the middle. So at the moment, let's assume that generator 1 is running. We call that the onboard machine. And so it's going to be showing 415 volts. It's going to have some sort of kilowatts on it. Let's say 220 kilowatts. Our frequencies going to be sitting on 50 Hertz. Okay, and here we've got two speed controls. So I can, in the manual setting, I can adjust my speed of my generator, which affects the frequency either by raising or lowering it. If I raise it, it's going to increase the frequency. If I lower it, it's going to lower the frequency. Okay. Now, when I'm ready to, if I want to bring another generator online, then I start up my generator 2 and it starts producing 415 volts. It should be somewhere around 50 Hertz as well. It's going to have no kilowatts because it's not on the board yet. Now, I can also adjust the speed of generator 2. This becomes the incoming machine. This one's on board, this one's incoming. And if I play with the speed control on my incoming generator, then it's going to adjust the frequency. Now, when we're synchronizing manually, what we want to do is increase the speed of our incoming generator just slightly above the speed of our onboard generator. And what that will do is get our synchroscope needle, works like a clock dial, and it will start rotating clockwise. If the incoming is slightly faster, it will rotate clockwise. If it's slightly slower, it'll be anti-clockwise. We want it going in the clockwise direction and slowly. So, and this sort of speed on our synchroscope, and the point to which our generators will be parallel or in sync will be at the 12 o'clock position. So we want the needle to synchronize at exactly 12 o'clock. Now, when we start, we increase the speed slightly on the incoming machine. It rotates slowly in the clockwise direction. And what's the accepted practice is to bring it online at about 5 minutes to 12. And that way it's got time to catch up, and it should be perfectly synchronized at the 12 o'clock position. So all we do is ensure that our voltage is right, set our frequency so that we get slightly faster, rotating in clockwise direction, and then we close our circuit breaker for the incoming machine at about 5 minutes to 12, and that should bring our 3 phases in sync with one another so that they start at the right phase at the right time and they're in sync with each other. If this is confusing to you, don't worry. When you come down to AMC, you're going to have a chance to practice this. We've got a simulator that you can synchronize 2 generators on.